This is the third and last lecture from Chapter 7, and this lecture will focus on orbitals and the quantum numbers that describe those orbitals. And to give you a quick review of what I mean when I'm talking about orbitals, the orbitals are something that came out of our most current model of the atom, which is the quantum mechanical model. And that was a result of, you may remember, hopefully, I said that Schrodinger developed these mathematical equations to describe the wave-like behavior of electrons. And when you solve Schrodinger wave equations, you get these three-dimensional graphs that represent orbitals. And this is an example of one. This particular one is, because it's spherical in shape, represents an s orbital. And to interpret these, basically the more dense the dot diagram is in a certain area, the more likely it is that an electron will spend its time there. So I'm going to give you just a brief overview of the types of orbitals that, or the shapes and types that come from solutions to Schrodinger's wave equations. The s orbitals are spherical in shape, and the higher the principal energy level associated with the s orbital, the larger in diameter the s orbital is. So what that simply means is if you have a larger diameter s orbital, the electrons that reside in that orbital are going to, in general, be farther away from the nucleus. P orbitals are typically described as dumbbell in shape, and unlike an s orbital, a spherical shape, no matter how you rotate it, it is going to look the same. A p orbital, on the other hand, as you rotate it, it's going to appear different. And so there are three p orbitals. They're equal in energy, but they have different orientations in space. And we have the d orbital, which gets kind of odd. D orbitals are typically described as clover shaped. There is this one funky one. You don't need to be able to draw or describe a d orbital, but there are 5 different d orbitals, again equal in energy, but with different orientations in space. All right, so this is an orbital energy diagram. And basically what I want you to get out of this diagram is the relative energies of the different types of orbitals we can have. So ultimately, next chapter 8, we'll be doing electron configurations, and so this will come into more play then. But the 1s orbital is the lowest possible energy orbital that is available to electrons in any atom, followed by the 2s, then 2p. So ultimately you're going to need to be able to memorize this ordering. Rather than drawing it graphically, you can also write it out as 1s, 2s, 2p, 3s, etc. And that's what we'll be doing when we get to electron configuration. So what I'm going to talk about now, though, is something called quantum numbers, and I want you to think about quantum numbers as simply an address for electrons in an atom, just like your address, which might be 1000 Chastain Highway, Ackworth, or Kennesaw, Georgia. The quantum numbers are an address for each electron in an atom, which gives us the energy level, shape of the orbital, probable location, etc. And so I'm going to go through each of the 4 quantum numbers now. The first quantum number is the principal quantum number, n, which we've talked about. So if you think about Bohr's model with the quantized energy levels, n equals 1 is the energy level closest to the nucleus, and n goes up by integers. One other thing I want to mention to you that's actually an important trend is look at this more accurate representation of Bohr's model at the bottom of the page, and look at the spacing between energy levels as you go to higher and higher n values. I'm hoping you see that the energy gap, for example, between n equals 1 and n equals 2 is quite a bit larger than the energy gap, for example, between n equals 6 and n equals 7. That's an important piece of information to tuck in your brain, because if you were asked a question, let's say you were asked to compare an electron moving from n equals 3 to n equals 2, and you were asked to compare that to the energy released when an electron moves from energy level 6 to energy level 5, which of these transitions would release more energy? I'm hoping you said between from the energy transition from 3 to 2, because the gap between energy levels 3 and 2 are larger than the gap between energy levels 6 and 5. Okay, my son's cat is trying to attack me while I'm making this lecture. The second quantum number is symbolized with a cursive L. It's called the angular momentum quantum number. And basically, the angular momentum quantum number describes the shape of an... All right, the second quantum number is kind of a cursive L. It's called the angular momentum quantum number. And that describes the shape of the orbital we're talking about. So, and for some reason, my figures didn't translate in this this video. So when you see a square, it should be a sphere. So L can have values starting with 0. It always starts at 0, moving up by 1s, but the highest L value that's possible is n minus 1. So for example, if n has a value of 2, the highest, well, the values L could have would be 0 and 1. And that would be, 1 would be the highest value L could have if n equals 2. So notice that L always has to be 1 less than n. So the other thing to remember is that if L has a value of 0, we are talking about s orbitals. If L has a value of 1, we're talking about p orbitals. And if L has a value of 2, we are talking about d orbitals. Not sure why I left f orbitals off this page, but if L has a value of 3, that is an f orbital. You don't need to know the shape for Fs. They're very complex. And here's just kind of a simple table diagram showing that. So make sure you commit these to memory, okay? Values of L and what type of orbital they correspond with. All right, onward to our third quantum number. That's m sub L. And I'm still thinking my font isn't supported here. So that's not a full size. The third quantum number is m sub L, the magnetic quantum number. And this one's gets a little bit more complex. I think this is the one that probably throws people off. So let me give you a little preview. If we are talking about an s orbital, which is spherical, you might remember, hopefully, that I said no matter how you orient a sphere, it's going to be the same. So an s sublevel has only one orientation in space, right? A p orbital, on the other hand, we found that you can orientate it 3 different ways, x, y, and z axes. So if you're talking about a p sublevel, there are 3 different ways they can orient. Okay, so kind of keep that in mind, and D had 5 different orbitals and F has 7. So keep that in mind as we go through this page. Okay, so the value of n sub L varies from minus L, that is an L, not a 1, to plus L. The values of m sub L must be integers. They always go through 0. 0 is an integer, okay? So, for example, if L has a value of 1, remember that hopefully from the last slide, that means we're talking about a p sublevel. And there are 3 p orbitals within a p sublevel. Let's see why. What are the values that m sub L can have if L is 1? M sub L has values of minus L to plus L going through 0. So if L is 1, the values that m sub L can have are minus 1, 0, and plus 1. 3 values representing each of the 3 p orbitals in a p sublevel. Let's think through that now. If L equals 2, what kind of orbital are we talking about? We're talking about a D. Now remember, we've learned already there are 5 d orbitals in a d sublevel. Let's see why. You'll see that as we go to the m sub l values. So the values m sub l can have, if we're talking about l equals 2, starts with -2, -1, 0, +1, and +2. My pen's not working. In other words, there are 5 m sub l values representing the 5 d orbitals that are possible in every d sublevel. If you're still confused about m sub l, don't worry too much. That's normal. And here's the 4th and final quantum number, m sub s. This is a simple one. It has to describe the spin of the electron. An electron can either spin clockwise or counterclockwise. Convention tells us if it's spinning clockwise, we give it a designation of +1/2. If it's spinning counterclockwise, we give it a designation of -1/2. We use arrows to designate the spin. So if you have this box representing an orbital, an up arrow would represent an electron spinning clockwise, and a down arrow would represent an electron spinning counterclockwise. Here's a recap on the 4 quantum numbers. I would write these on a note card or a separate piece of paper so that you can refer to them. Principal quantum number has integer values. L, the angular momentum quantum number, has values starting at 0, going all the way up. The highest value is 1 less than whatever n is. Magnetic quantum number, m sub l, has values from -L up through 0 to +L. And spin quantum number, m sub s, can either be +1/2 or -1/2. Looking at it graphically, if you're like me. Alrighty, so here is a graphical way to look at it. This way makes a little more sense to me, so in case it helps you. So summarizing again, if we're talking about principal quantum energy level 1, which corresponds to the first row of the periodic table, L can only have a value of 0, which means that in the first row of the periodic table there are only s orbitals. And m sub l tells us that there is only one type of s orbital. If we go to energy level 2, or period 2 on the periodic table, we can now have L values of 0 and 1. In other words, the second period on the periodic table has S sublevels and P sublevels. Remember, every S sublevel has only one orbital in it. Every P sublevel has 3 p orbitals in it. So you can think of the m sub l as telling you the number of orbitals, okay, in a sublevel. All right, and finally, energy level 3, the third period down on the periodic table, can have S sublevels, P sublevels, and D sublevels. I want to point out something here that has helped me in the past. It's just kind of a little memory trick. But notice, I'm hoping that you notice how many sublevels there are within each main level. So energy level 1 has only one sublevel, and it's S. Energy level 2 has 2 sublevels, S and P. Energy level 3 has 3 sublevels. So the number of sublevels equals the energy level. This slide is really a different way of showing exactly what we just went over in the last slide. Basically, that first energy level only has one sublevel, and it's a 1s. Second energy level has 2 sublevels, S and P, and we call them 2s, 2p. Third energy level has 3 sublevels, S, P, D, so they're called 3s, 3p, and 3d. This is a handy dandy compact slide showing you all the different values that the 3 out of the 4 quantum numbers can have. So if you can interpret this one at this point, you're doing really well, and you might want to jot this down. So basically what this is, the n value, the values that L can have if n equals 4, the values that m sub L can have for every L value, and then the orbital designation for those quantum numbers. Okay, so I would take a minute, I'd turn off the video, take a minute, make sure you can interpret this, because this is kind of the ultimate goal of everything I've talked about so far. Here's a sample problem that you might see on a quiz or test. Which of the following orbitals shown down here, these 4 orbitals, could have the quantum numbers given right here? So I would recommend turning off the video and seeing if you can rationalize your way through this on your own. And then I will go through the rationale that I would use. All right, so we were told that the n value has to be 3, so we're talking about the 3rd energy level. So immediately we can cross out any orbitals that are not in the 3rd energy level. So it has to be one of these 3, if not all of them. Then we go and look at the L value. If L equals 2, what type of sublevel or type of orbital are we talking about? We are talking about D sublevel. So we can immediately cross out the S and P. And so the only one that matches all of these quantum number designations are the 3D orbital. Let's make sure the M sub L is okay. Let's see, if L equals 2, if we're talking about a D sublevel, the values that M sub L can have are -2, -1, 0, +1, and +2. So that 1, an M sub L value of 1 is perfectly fine for a 3D orbital. And here is another common problem. Which of the following orbital, this should say designations, are theoretically possible? So I want you to go through each one of these and see if it's possible to have an orbital with these quantum number designations. So I again would recommend turning off the video and seeing if you can do it yourself. So I'm going to go through the rationale now. In energy level 7, so if n equals 7, the values that L can have are 0, 1, 2, 3, 4, 5, and 6. S means L equals 0. That's perfectly acceptable. So A is a theoretically possible combination. B, if n equals 1, the values that L can have are only 0, because L goes from 0 up through 1 less than n. So if L is 0, we're talking about S orbitals only. So there are no P sublevels in energy level 1. All right, looking at C. If we're talking about n equals 5, the L values possible are 0, 1, 2, 3, and 4. We got to stop at 1 less than n. And so in the 5th energy level, we can have S, P, D, F, and some crazy level. So we can have D sublevel within n equal 5. So C is possible. D, if n equals 2, the values of L are 0 and 1. In other words, we can only have S and P sublevels if n equals 2. So no D levels, no D sublevels in the 2nd energy level. Let's look at the last one for F. If n equals 4, L can be 0, 1, 2, and 3. So in the 4th energy level, we can have S, we can have P, we can have D, and we can have F orbitals. So 4 F orbitals perfectly fine for the 4th energy level. So A, C, and E are all allowed. B and D are not. All right. One last question for you. What are the possible m sub L values for each of the following orbitals? Now notice whenever you're talking about SPDF, you're really talking about L values for quantum numbers, right? So if you have an s orbital, what is L? L is 0. If you have a p orbital, you're talking about L is 1. A d orbital, L is 2, and an f orbital, L is 3. So this question is saying, what are the possible m sub L values? Well, if L equals 0, n sub L is also 0. If L is 1, the possible m sub L values are -1, 0, and +1. If L is 2, the possible m sub L values are -2, -1, 0, +1, and +2. And finally, if L is 3, the possible m sub L values are -3, -2, -1, 0, +1, +2, and +3. So that is your answer for this one. And I lied. There's another question. I thought that was it. How many possible orbitals are there if n equals 4? I'm going to show you the long, laborious way and then the shortcut way. So if n equals 4, what are the values that L can have? L can have values of 0, 1, 2, and 3. So that's S sublevel, P sublevel, D sublevel, and F sublevel. The number of orbitals are given by m sub L. So if you didn't get that down earlier, put it down now. The number of orbitals in a sublevel are given by m sub L. So let's look at the m sub L. If L is 0, m sub L also must be 0. That's it. So there's only one m sub L value, or one orbital, in a S sublevel. If L is 1, if it's a p sublevel, the values of m sub L can be -1, 0, and +1. In other words, there are 3 m sub L values, or 3 orbitals, if we're talking about a p sublevel. All right, so if we are talking about a d sublevel, in other words, L value is 2, the m sub L value is -2, -1, 0, +1, +2. So in other words, there are 5 orbitals possible in a d sublevel. I'm not going to go drag you through the painful list, but if we did the same thing with F, we would find that there are 7 orbitals in every F level. So this question says, how many possible orbitals, stick with me because I'm going to give you the shortcut at the end, how many possible orbitals if n equals 4? How many do we have so far? We have 1, let me change colors here, plus 3, plus 5, and then up here for F, plus 7. So how many is that? 1 plus 3 is 4, plus 5 is 9, plus 7 more. So there are 16 orbitals possible if n equals 4. Okay, here's the big reveal. What is the relationship between energy level and number of orbitals? What's the relationship between 4 and 16? This is huge, guys. This is going to save you at least 5 minutes on a question like this on the test. I'm going to open up a new page to show you. Here we go. So the number of orbitals in an energy level equals n squared. All right? So if energy level 1, the number of orbitals is going to be what? 1 squared, 1. And that's true. There's only an s orbital and n equals 1. N equal 2, the number of orbitals is 2 squared, or 4. Okay, there's one s and there are 3p. That gives you 4 orbitals. Oh, it might be worth going and listening to the last couple slides a few times, because this is like the pinnacle of everything. If n equals 3, there are 3 squared, or 9 possible orbitals. What are those 9? There's always one s, there's 3p, and now in the third energy level you have d's. There are always 5d. So what is 1 plus 3 plus 5? It's 9. Okay. So now you can answer that last question. That is a made-up energy level, 10. If n equals 10, how many orbitals? You don't have to go through this big old mess. Okay, the number of orbitals is n squared. What is 10 squared? Okay, there are 100 orbitals if there were an energy level of 10. Okay. And guess what? That's it. Almost. Well, almost it. Kind of going in the reverse direction. If I gave you pictures of orbitals and said, come up with the quantum number designations for those, hopefully you would be able to do this. The only thing that might be a little bit different is, what if I gave you 2 spherical orbitals with different diameters? How would you assign them? Well, I mean, you could have called them 1s and 2s. It doesn't really matter. But as long as you realize the larger the diameter, the higher the energy level. Same thing with the p orbitals here. So that is it for Chapter 7. We're going to move on to electron configurations next.